University of Cambridge.
Where's the clicker? Maybe I took it with me. So thanks and good morning, everyone. Ooh. Thank you for the invitation to be here. It's a nice workshop and a slightly different crowd from one I'm used to addressing. So if there are things that I say that don't sound familiar, then please just ask. Yeah, so I think I was asked to speak for 45 minutes or so. I don't think I'll probably manage quite 45 minutes. But I have to say no one's complained in the past when my talks are finished early. Okay, so isotonic regression in general dimensions. This is joint work with three excellent collaborators. Roy Hun from the University of Washington, a PhD student of John Wellner's. Tengyao Wong is my fantastic former PhD student and postdoc. And Sabyasachi Chatterjee, who was at Chicago for most of this project and has just moved to University of Illinois. Okay, so isotonic regression, isotonic you can think of as a synonym for monotonic. So if that was the first word that was confusing you. This is perhaps the simplest and most widely studied form of shape-constrained estimation. To set the scene, shape-constrained estimation is a field that's been around in statistics for 60 plus years now, but it's undergone a real renaissance over the last 10 and especially over the last 5 years. So people like to look at problems like estimating regression functions or density functions in a non-parametric way, but under qualitative shape restrictions. So this would be a sort of contrast to more typical methods and analyses that are based on smoothness assumptions. And the particular attraction of working with shape constraints is that often you can end up with procedures that don't require the choice of any tuning parameters. That's very unusual within non-parametric statistics, and I think gives you sort of canonical ways of estimating functions and a whole lot of very interesting theoretical problems, as well as ones that I think have significant practical applications. But in the simplest version of this isotonic regression problem, we're simply trying to estimate a monotone regression function from noisy observations at an ordered set of design points. So this project is not really motivated by one particular application area, but I think it's not too difficult to think of many different application areas where you can imagine it would be reasonable to model a response or a mean response as a monotone function of one or more covariates. So certainly in economics, it's very standard to assume monotonicity for utility functions and things like that. I think in a lot of biomedical applications, genetic examples, these are very reasonable assumptions. So I'm going to be interested in the multi-dimensional setting, so where we've got several different covariates. Actually, this has been studied quite a lot in the genetics literature, where, as I say, there are lots of cases where you might think that phenotypes are monotone functions of covariates. If you have many different covariates, it's kind of desirable to try to think of some simplifying structure, the simplest of which would be an additive structure, but several others of which have been also studied. But these have often been found to be too restrictive. And so in this talk, I want to think without assuming some additive or low-dimensional structure within the isotonic function, how can we try to estimate this? Okay, so if we are working with covariates on R to the D, then we have a natural partial ordering. I'm going to be thinking about the set of block increasing functions, so just increasing in each coordinate. And I'll write the class of block increasing functions as curly FD. And then our basic problem is, let's assume that we have independent observations, so covariate response pairs. Our covariate is xi and takes values in 0, 1 to the d. And our response yi is real valued. And I'll think of this simple regression model where we can write yi as f0 of xi plus some error epsilon I. And for simplicity, throughout this talk, I'll just think of my errors as being standard Gaussian, having a standard Gaussian distribution. That's an assumption that could certainly be weakened, but it's not really the main focus of this talk here. There are sort of two classes of problems here. One is where we might think of covariates as being fixed and the other as random. And there are different applications where each might make sense. Let's say we were doing some sort of chemistry experiment and we wanted to look at the way in which a rate of reaction depended on the concentration of some catalyst that we were putting in to our experiment. Then we would predetermine the concentrations of the catalysts that we were going to try to measure the rate of reaction at, and so it would be natural to think of those as fixed in advance. On the other hand, if you were a doctor and you were measuring, say, the heights and weights of patients who came into your surgery, then it would be more natural to think of the covariate as being random. So both fixed and design regression problems crop up in applications, and we're going to study both here to kind of preface what will happen later. The fixed design case is actually, from a technical point of view, somewhat easier to study. Okay, so I'm going to think about the simplest estimator you could possibly think of within this class, which is just the least squares estimator over the class of block increasing functions, over this class curly FD. So one thing that you'll notice immediately about this definition is that I'm only constraining the values of the estimator at the observed design points. So there's a sort of non-uniqueness in the way that I might extend this function to belong to the class curly FD. That's not really too much of an issue for us because actually the risk, the sense in which we're going to measure the loss here is in terms of its empirical risk, so we're only going to measure the loss at the observations. There are very natural ways you might think of the kind of, say, the smallest function that belongs to this argmin. Okay, here's one more observation that whether we're in the fixed design case or the random design case, our design points form a DAG, a directed acyclic graph, with respect to this natural partial ordering. I should perhaps have said that in the case of the fixed design, my focus is going to be on the case of a lattice. So this simple lattice like we have drawn here. But even in the random design, I can think of the partial ordering on the design points induced by the natural partial ordering induced by the design points and the DAG. Okay, so if we're going to think about feasible vectors within that satisfy all the monotonicity constraints that we require, we can think of them as lying in the monotone cone. So this is an intersection of half spaces, and I'll write that monotone cone as curly M of G. So I don't want to focus too much on computation in this talk, but just to mention that this least squares estimator is computable. So you can use something like Dijkstra's algorithm. So if I've got, let's say I've got two different half spaces. Maybe I'll draw this with a different color. So if I want to project onto the intersection of these different half spaces, I can think about the polar cone that looks like this. And the most naive algorithm, which would be sort of von Neumann's algorithm, would say, if I start with a point here, then I would project onto one and then project onto the other. But what you immediately see is that that's projected onto the wrong point. Right? This was the closest point within the intersection, and my algorithm would sort of terminate here because I belong to the intersection, but I'm not at the closest point. There's an alternative called Dijkstra's algorithm, which allows you to, you project, and then you come back like this, and then you reproject. And the kind of memory means that you do indeed converge to this optimum here. Or you can use interior point methods as well. Okay, so there has been a lot of work on the basic isotonic regression problem, but almost all of it has been confined to the univariate design setting. So this is a problem that goes back more than 60 years now. But then there have been several results on rates of convergence, and more recently on oracle inequalities. And I'll say more about that later on in the talk. There's another recent paper by Chatterjee, Gundabuyina, and Sen that looks at the bivariate case for the fixed lattice design. And then there are other sorts of results that do work within sort of these simplifying structures, and the simplest of which would be to assume you've got an additive model for your regression function. But that's a sort of separate line of work to the direction we're going in this talk. Okay, so let's focus on the case of a fixed lattice design, and let's suppose that our covariates take values on this grid. And so I'll think of, just for simplicity again, I'll think of my sample size as being a dth power of an integer, and I'll say it's a dth power of n1. Okay, well in that case I can think of my sort of true signal vector as being theta 0, and my estimator as being theta n hat. That's just the least squares estimator at the observed design points. And then my risk function I can think of as being a function of theta n hat and theta 0 rather than fn hat and f0, and it's just going to be the average squared error that I make on the design points. Okay, so if I want to compute the least squares estimator, I have to think about projecting my response vector y1 up to yn onto this monotone cone, this intersection of half spaces. And there's a very beautiful recent result due to Saurav Chatterjee. So there are two different S. Chatterjees involved in this work. There's my collaborator, Sabyasachi Chatterjee, but this is a different one. This is Saurav Chatterjee, who's at Stanford. And so this is his characterization of the least squares projection onto a convex set. And here's what the result says. I think it's a very beautiful result. Let's suppose that mu belongs to a closed convex set K, and that epsilon is our error vector. So essentially it says that the risk of the projection of my observation onto the convex cone is characterized by this quantity T0, where T0 is the maximizer of this this expression here. So this is like the supremum of a Gaussian process. This isn't working very well. I wonder if this will work better. Okay. Right. A smart screen that's not so smart. Yeah, so we're looking for the maximizer as sort of expected supremum of some Gaussian process, and then we're subtracting this quadratic term. So if you think about this quantity here as a function of t, let's say mu is in the interior of my convex set, then because of the way that this sort of bilinearity of the Euclidean inner product, this is going to increase linearly in t to start with, and then you're sort of penalizing it with this quadratic term. So it's 0 when t is 0, but then because of the linear thing, it's going to be increasing to start with, but then eventually this quadratic term is going to win the race, and it's going to come down. And actually what you can show is that this is a strictly concave function that tends to minus infinity. Okay? But if we can locate the maximizer of this function as a function of t, and if this maximizer is greater than or equal to 1, then the risk of my least squares projection onto this closed convex set is essentially given by so if I'm looking at a squared error, then it's given by the square of t0 up to some error term that I can quantify. I think it's a very attractive result. It's very unusual to get also lower bounds on risks. So it's really nice to see that we're not losing anything here. Okay. So here's a picture to have in mind. And what is sort of obvious from the picture is that if I can find any upper bound t star for where I'm crossing the x-axis here, then certainly that's going to be an upper bound on t0. Okay? So if I want to bound the risk, then I can say it would be less than or equal to t star over n for any point t star which is beyond the point where that function crosses the x-axis. Okay? So my strategy is going to be to try to find an upper bound for this point here, and therefore to bound the risk. Okay, so let's suppose that I fix some vector that belongs to the monotone cone, and then my notation here is just saying that every component of theta 0 in absolute value is bounded above by 1. So it belongs to the L infinity ball of radius 1. Let me write theta 0 bar for the constant vector with each entry equal to the average value of the signal over the entire lattice. And then I'm going to try to rewrite the left-hand side of this guy. So I'm going to bound this left-hand side above, and then if I can find anything that satisfies that inequality, any t star that satisfies that inequality with an increased value of the left-hand side, then I'm still okay. So let's bound the left-hand side above. I'm going to decompose this in a very obvious way by just subtracting and adding the theta 0 bar. But then I notice that this term doesn't have any dependence on theta, so I can pull it out of the supremum. And moreover, the expectation of this term is 0, because the expectation of epsilon is 0. Okay? So I can forget about that term. And then I can say, well, if theta minus theta 0 is less than or equal to t star, then theta minus theta 0 bar is not that much larger, because I know that theta 0 belongs to this L infinity ball of radius 1. So I just have to increase this radius by n to the half, and then I can rewrite this as a theta minus theta 0 bar. Sorry. And then the crucial point here is that this set is closed under subtraction or addition of a constant vector. So I can just translate this and talk about, now this is saying I'm working within the L2 ball, centered at 0 and of radius t star plus n to the 1/2. Okay, so that's just the fact that the class of monotone functions is closed under addition of a constant. Okay, so we've got this sort of Gaussian process here, and then this is linear in this argument here, so I can pull that guy out of the front and work within a ball of radius 1. And then I could just use Cauchy-Schwarz to bound this sort of first moment by a second moment to the power of a half, where the second moment's got a special name, And it's called the statistical dimension of the monotone cone. Who's come across the idea of a statistical dimension before? So this is a quantity that turns out to be very important in these sorts of problems, has many different equivalent definitions. There's a very nice paper that I'll mention several times, I think, due to Amelunxen et al. From a few years ago called Living on the Edge, that presents a lot of properties of statistical dimension and illustrates its power in these types of problems. Anyway, so once I put all this together and I compare this with what I had on the previous slide, I just solve for t star. I've got to solve a quadratic equation, and I can see the way in which now the rate is driven by the statistical dimension of this monotone cone. Okay. Okay, so what's known about the statistical dimension of the monotone cone? There's a very nice result in one dimension that's again in this Amelunxen paper, that the statistical dimension of the monotone cone in one dimension is exactly equal to the sum of the first n terms of the harmonic series. So it's basically log n. And then in the bivariate case, it's also known that it behaves polylogarithmically in n. But in higher dimensions, nothing was known about this. And the key idea is to sort of inductively reduce dimension one at a time. So what you can imagine doing is you can take your lattice and you can divide it into slices, and then you can imagine removing the constraints that are between the slices. Okay, so that's removing constraints. It's enlarging the statistical dimension of the monotone cone, and then I can use basic properties of statistical dimension to say that I just have to add up the statistical dimensions of the corresponding lattices, and because I've got n to the 1 over d of these different slices, then each time I reduce dimension by 1, I have to inflate the statistical dimension by a factor of n to the 1 over d. So I keep going down, but I should stop at 2. I shouldn't go all the way down to 1, because I know that the statistical dimension behaves polylogarithmically in n when d is 2. I don't want to incur another penalty of n to the 1 over d by going down to d is 1 here. And this is something that we know how to control once we've got down to d is 2 using Dudley's entropy integral. And so we have the following result, that the statistical dimension of the monotone cone in d dimensions, of the cubic lattice in d dimensions, I should say, is essentially n to the 1 minus 2 over d. So the squiggles on the bottom here are disguising universal constants. And I'm also not going to worry too much in this talk about polylogarithmic factors here. So I'm really thinking of this as being basically n to the 1 minus 2 over d. So, okay, that means that we can just plug that back into this formula and get a bound on the risk of the least squares estimator. And here's what we find, is that for every d greater than or equal to 2, we can find a universal constant for which the risk of the estimator is bounded above by n to the minus 1 over d up to polylogarithmic factors. Okay. And moreover, you can't beat this result in a certain sense. So if you forget about the polylogarithmic factors, then here's a minimax lower bound. Who's familiar with minimax lower bounds? So here I'm taking, it's the same sort of supremum, but here's an infimum over all estimators. So here I was looking at the risk of a particular estimator, the least squares estimator, and here this is saying the best any estimator could do, if I take an infimum over all estimators here, is not much better. It's a lower bound, of course, so it's got to be smaller than this one, and it gets rid of the logarithmic factor. But other than that, we've got the same bound there. Okay, so to a statistician, that's sort of solving the problem. Okay, so yeah, maybe I should say something about how you come about this lower bound. The idea, this is a kind of key idea perhaps of our work, is that this lattice has a large anti-chain. So a chain is a set of mutually comparable vertices in this ordering. An anti-chain is a set of mutually incomparable vertices. Okay? And the point is that this lattice does have a large anti-chain that's illustrated here. It's basically all these points on the anti-diagonal of my lattice. So you'll notice that, let's say, if I take 2 points that are at the same level, vertical level, I can't compare these points because one is larger in the x direction and the other is larger in the y direction. And similarly, for any pair of points here, it's not too difficult to see that they're not ordered within this monotone cone. So what that means is that you can construct a lot of different binary vectors within this monotone cone. They could say each be 1 above this diagonal, each be 0 below the diagonal, so they look very similar on a large set, but you've still got this large anti-chain, and you've got complete freedom to choose whatever values you like for the signal on that anti-chain. And that sort of puts you in a good position to use one of the kind of standard techniques for coming up with minimax lower bounds, which would be Assaward's lemma. Okay. So there's a very interesting and I think very surprising overall picture here. So these results in 1 and 2 dimensions were already known. And those, perhaps you could say, were the sort of expected rates. So the basic idea is that a monotone function is differentiable almost everywhere, and therefore you should expect to get the same, I mean, the sort of intuition here is that you should expect to get the same rates of convergence as if you had one bounded derivative. Okay, so it's like having Hilda smoothness 1. And that would give you a rate in general of n to the minus 2 over d plus 2. But what we're finding is that in higher dimensions, you actually get a slower rate than would be predicted by that. You get an n to the minus 1 over d. And it's caused by these two sort of competing factors, one of which you can think of as being the length of the longest chain, which is basically related to the sort of smoothness properties of bounded Lipschitz functions or bounded Hilda 1 functions. And then on the other hand, you've got the large anti-chain. So in 1 dimension, it's this guy that dominates. In 2 dimensions, they actually turn out to have the same contribution, both giving this rate of n to the minus a half. But in the higher dimensions, it's the anti-chain that is the more constraining factor and that leads to the slower rates of convergence. So this theta tilde, that's hiding the logarithmic factors here. And the other particularly surprising thing about this result, which I think for people who know a bit about empirical processes has come as a really big surprise, is that we're seeing that a global empirical risk minimization procedure here, just ordinary least squares, can be minimax optimal, at least up to polylogarithmic factors, even over classes where the entropy integral diverges at some sort of rapid rate. So there are some negative results in a very well-known paper due to Birger and Massart from over 20 years ago now, where they show that if you're just looking over Hölder classes, that a global empirical risk minimizer cannot attain the minimax optimal rate once the entropy of your class grows like this, which means that when you try to integrate the square root of that, it's diverging. And so people have kind of taken those results and inferred that you shouldn't use. I mean, that's really a counterexample in some sense. But people have generalized that and come to the conclusion that you shouldn't use global empirical risk minimizers as soon as the entropy integral diverges at this rate. Are people familiar with entropy integrals? Yeah. But what we're seeing here is an example where even though this entropy integral does diverge rapidly, we are still attaining the minimax optimal rate up to polylogarithmic factors. So I think that's the first example where that's been seen, and I think it'll be very interesting to see to what extent this is sort of typical behavior, and to what extent there's really something exceptional going on here. And I think for theoreticians, there's something really to try to get one's teeth into here. Okay, so I've talked about worst case bounds so far. And now I want to come on to talk a bit about adaptation. So very often in statistics, we're first of all interested in worst case bounds, sort of minimax rates of convergence. But often within parameter spaces, there may be smaller subparameter spaces of functions that have particularly simple structure. And so the simple structure I'm thinking of within the class of monotone functions is the class of functions that can be written as where the signal is sort of constant on a relatively small number of hyperrectangles. Okay? So the simplest possible case would be where your regression function is itself constant. Now, that I think of as being a signal of particularly simple structure, because if you told me in advance that the signal were constant, more generally, if you told me it was piecewise constant with only a relatively small number of constant pieces, then I could estimate differently. I mean, in the simplest case, where it's constant, I would just use the sample mean of my observations to estimate the piecewise constant, the constant signal. And then I would know what rate I could get, right? On the squared error scale, I'd get a rate of n to the minus 1. And the question is, can the method where I'm looking at least squares estimation over this much larger class, I'm agnostic to the potential for the signal to lie within a smaller class, but is it possible that I can do nearly as well as if you told me in advance that I was in the smaller class? Okay, that's the sort of philosophy behind adaptation. And here is a result of this sort of form. So I'll write curly mk for the collection of signal vectors within my monotone cone, for which I can partition my lattice into hyperrectangles, k hyperrectangles, and the signal is constant on each hyperrectangle. So here's a result that I call it a sharp oracle inequality, and I'll explain that in just a moment. But it says that I can bound the risk above by the infimum over all k, and the infimum over thetas within this class are a sum of two terms, which I can sort of think of as an approximation error term and an estimation error term. Here's my approximation error term, and here's my estimation error term. So the simplest possible case here would be, let's say that the true theta 0 is constant. That means that k is 1 here. This term I could then think of as vanishing, and I'm getting an adaptation rate of n to the minus 2 over d instead of n to the minus 1 over d, again ignoring the logarithmic factors. So I'm getting a faster rate of convergence than I would have had over the larger class. And I can see the way that this increases with k. So provided k is relatively small, I'm doing better than the worst case rate. It's called a sharp oracle inequality because the leading constant in front of this approximation error term is 1. There's no kind of universal constant in that term. And writing in this way, I mean, you see, for instance, let's suppose that I could write it my signal as piecewise constant on k pieces, but it was very close to being piecewise constant on k minus 1 pieces. So there was only a very small difference between the signal levels. Then actually, this term might be smaller than the additional contribution I get from the reduction I get by thinking of this with a k minus 1. So I can take the infimum over all things here, which is kind of nice. The way that these two terms trade off against each other. Any questions about that result? Okay, and here's a sort of a lower bound. It's a different form of lower bound from what we saw before. This is not a minimax lower bound. I'm not taking an infimum over all estimators here. I'm just looking at this particular estimator, the least squares estimator, and I see that essentially this rate that I'm getting from this term here can't be improved. So even in the constant signal case, where the true theta naught is 0, when d is 2, the lower bound is n to the minus 1, and actually it's kind of nice that I've got logarithmic factors here. That's sort of improving the lower bound. I'm getting a larger lower bound. Some logarithmic penalty is necessary. And when d is greater than or equal to 3, it's n to the minus 2 over d, which is matching. So in the case where k equals 1, that's matching the rate that's being given by this term here. So again, if we're to look at these results, when we're in the low dimensional case where d is less than or equal to 2, I can adapt at parametric rate up to polylogarithmic factors in 1 and 2 dimensions. So I'm doing almost as well as if you actually told me that the rate was piecewise, the signal was piecewise constant, even though I didn't know that at all. The estimator didn't know that at all. In the high dimensions, I do get faster rates than I had in the worst case, but I'm not getting the parametric rate. Okay? These are slower rates. This is a sort of strictly non-parametric rate of adaptation here. So we are getting the minimax rate over the large class, but we're not getting the minimax rate over the small class. So it would be an open question as to whether there were another estimator, for instance, that could simultaneously attain these optimal rates over both the large class and the small class. Any questions?
So, when in the previous thing you have this approximation by piecewise constant over rectangle, what type of smoothness property govern the decay with k of this? If you want, I don't know, if you ask what rate you receive from this, if theta has a certain amount of smoothness. If theta has a certain amount of smoothness, like mixed Holder smoothness or something, you might be able to say something about this approximation term. And how to balance.
So I'm not making any assumptions about the smoothness of the signal, only that it's...
Yes, but now you have an approximation term.
I do have an approximation term, yes.
So if the signal happens to have a certain smoothness, you might be able to say something about...
Yes. So I should think of monotone functions as being a little bit like bounded Lipschitz functions. So it sort of hold a 1 smoothness in the one-dimensional case anyway.
Really? The monotone function can have jumps.
That's right, but they're nevertheless differentiable almost everywhere. And if you were to look at the entropy of the classes in say, in one dimension, it would be the same as if you have hold a 1 smoothness.
In addition to being monotone, you have something about the derivative or something intermediate, or can you infer something? Maybe I'll ask you later.
If you have less than or equal to 1 smoothness, that doesn't help you. If you have more than 1 smoothness, then it's the smoothness itself that would drive things, and the monotonicity wouldn't help you. Okay, so now let me say something about random design. So I'm going to think about the case where my design distribution is uniform on 0, 1 to the d. I can weaken this assumption somewhat if the design distribution has a density with respect to Lebesgue measure that's bounded below by a positive constant and bounded above by a positive constant. I could get very similar sorts of results, but let me just focus for simplicity on the case of the uniform distribution. And now my risk function I do need to think of as being a function of fn hat and f0, and I can write that as an expectation of the L2pn squared loss, where pn here is the empirical distribution of the design points. There's a typo here, this should be an n. Okay, so essentially the results are very similar in form to what we had in the fixed design case. We again see a worst case rate of order n to minus 1 over d. The logarithmic exponents are a bit different, they're a bit worse in the random design case than the fixed design case. And we also get a sharp oracle inequality of a similar sort of form to what we had before in the fixed design case. But even though the results look very similar, I have to say that the proofs are significantly more challenging in the random design case. So to give some sense of this, if you look at the class of monotone functions, you have an L infinity truncation as well. Then the regular entropy is of order epsilon to minus 2 into d minus 1. And so if you were to use a standard chaining argument, you would get a suboptimal rate of n to the minus 1 over 2 into d minus 1 for the risk. As I explained in the fixed design case, what we were able to do is to decompose each of the lattice into slices and then think about removing the joins between those slices. We don't have that sort of regular structure in the random design case, and that's part of what makes things significantly more challenging. A very basic sketch is to start by looking at the adaptation risk when f0 is 0. And you can approximate the L2pn squared norm of fn hat by the L2p norm over the when you've got an L infinity truncation. As always, in some sense, with least squares problems, you're going to start from a basic inequality. You say that your risk, which I can write like this, of your estimator fn hat, or at least the loss is smaller than the loss at the truth, which gives me the epsilon squared there. And if I rearrange that, it tells me a way of bounding this p of fn squared, which is the same as this guy here, which is what appears in here. And then, so I can see that basically to control this guy, I want to control this one and this term, and this is, so gn, this is just the empirical process, it's root n times this one over here. And really, if you can control this one, then you're done, because that's essentially the same argument. So we've reduced things to trying to think about controlling this type of empirical process here. And here is the game. We're again going to divide things into slices. And even though we don't have a kind of fixed design where we know exactly how many joins we're removing and things, with high probability, we know how many data points lie within each slice, and we can therefore control with high probability the size of the largest anti-chain, and moreover, we've got control of the how big the envelope function for the class can be within each slice, and that decays, because I know I'm working with a class of decreasing functions, that decays in L by a power of L to the minus a half. So that's just a very sort of quick sketch of how we prove things. And then the corresponding sorts of results here that we again have a minimax lower bound over the class and a lower bound on the risk of the least squares estimator at 0, just sort of paralleling what we had in the fixed design case. There's something kind of interesting here. Let's say you're in the d equals 2 case, and you want to think about the largest anti-chain that you have. So I can think of one coordinate as being ordered, and then the size of the largest anti-chain would be, say, the size of the length of the longest decreasing subsequence within a uniform permutation of 1 up to n. Okay, so this is something that probabilists have studied an awful lot. And there's a very nice result called the Erdős-Zechari's theorem. And it says if you have a sequence of length r minus 1 times s minus 1, and you add 1 to it, then within that sequence there must be an increasing subsequence of length r or a decreasing subsequence of length s. Okay, I think there's been a lot of work done by probabilists on length of longest increasing or decreasing subsequences of uniform permutations. So we were able to borrow some of that theory here. Okay, so let me wrap up and say that isotonic regression behaves rather differently when, well, you could say d is 1 and d is greater than or equal to 3, and d is 2 is a sort of transitional case here. We have a worst case rate and an adaptive rate in the fixed design case, and similar behavior in the random design case. I think there are still lots of open problems. So how can you study isotonic regression on a general DAG? So let's say where you have fixed but non-lattice design. Can you deal with other global loss functions, particularly in the random design setting? What can you say about point-wise rates of convergence? So how well you're doing at a particular point rather than globally. What can you say about other shape constraints in general dimensions? I think it's particularly interesting to ask, are there other settings in which empirical risk minimizers can attain minimax optimal rates, even when entropy integrals diverge? Okay, so the paper has now been on the archive for about 3 or 4 months, and this is the main paper on which that works based. Thank you very much for your attention.
Okay, thank you very much. Questions for Richard?
So in all these results, you have this 1 over d coming up because you don't assume anything more in a way. You're sort of doomed with the curse of dimensionality. I mean, if you are in dimension 100, you are in deep trouble.
Yep.
Okay. So now, if you have assume more, like you could assume many different things, like some kind of fading effects in certain variables that are less and less active in some ways that you could quantify, or that only a few variables but which are unknown to you are the active one. Can you benefit from that? I mean,
I'm sure you can.
Will your method somehow detect this and take advantage of this automatically? Or do you need to cook up another method?
I think for those structures you mentioned, you would need another method. What the structure that we can show the least squares estimator does adapt to are ones that are piecewise constant with relatively small numbers of constant pieces. But if, as you say, the true structure is additive So you can decompose f of x1 up to xd as a sum of fj of xj, for instance. Then you might hope to get univariate rates or something close to univariate rates even in general dimensions to avoid the curse of dimensionality. So I think there are several different structures one could think about imposing, but this is as far as we got with this work.
Okay, any more questions? So I have a very simple question. So do your results still hold in the case where you don't have any noise in the observations? So if the epsilons are 0? Maybe it's not a simple question, I don't know.
So that's essentially an approximation theory question as opposed to a statistical question. Yeah. Let me think about this. How would I expect the noise to enter here? So I should get, in general, if I had normal 0 sigma squared noise, I think I would get a sigma squared term appearing in this term here. Yeah, that's what I would see there, I think.
Thanks for the talk. That was great. First, maybe a comment, maybe to strengthen your case for monotonic or isotonic regression. In engineering, the engineers often make these sort of like back of the envelope kind of statements of, if I add more of X, I get more of Y. So if you get like an engineering data set, then I would think this would be a really useful tool.
Mm-hmm.
But maybe along those lines, you're saying, I believe that there is some monotonicity in my data set. I'm going to use this model that sort of supports this monotonic structure. Is there a way to take a data set that you believe is somehow noisy or error corrupted and test for monotonicity within that data set?
I do know that there are one or two different approaches to this. I think the only work I'm familiar with is with univariate covariates. But one sort of test you might use is you could think about fitting, let me think about this. No, perhaps that's a slightly different problem. But there do exist tests of monotonicity, I think, but I think I only know about them in one dimension. But that's another related and interesting question.
So then the other question that I had was regarding this least squares problem. You didn't talk much about the algorithms for solving the least squares problem. It seems like that class of functions, script f sub d, is a nasty class of functions to optimize over. Like, do you parameterize it somehow? How do you end up doing this least squares problem?
Just what I was saying here, I mean, there are two basic different approaches. One would be Dijkstra's algorithm. So this kind of variant of von Neumann's iterative projection onto the different convex cones, or onto the different half spaces, or you can use interior point methods. So it is a feasible optimization problem, even in pretty high dimensions.
Thanks.
I was just wondering, I mean, it seems like your estimate's going to be more accurate where you have more data. So is it easy to do uncertainty quantification for this estimator?
So the only work I really know of on uncertainty quantification, it's a very nice, very recent paper, is by Fan Yang and Rina Feubel-Barber, but that's again for univariate covariates. So the most obvious approach would be to try to study the asymptotic, the pointwise asymptotic distribution of the least squares estimator at a general point x. And you would probably want to assume that the function was, say, continuously differentiable in a neighborhood of that point and had a non-vanishing derivative. the trouble then would be that so in the one-dimensional case, you'd have an n to the minus a third rate of convergence at that point. The trouble is that the asymptotic variance depends upon things you don't know, the sort of derivative behavior of f. And so then you'd have to try to estimate it if you wanted to get some sort of confidence interval or something like that. So I think more attractive approaches are based on inverting likelihood ratio statistics. And that way you can get sort of distribution-free asymptotic results. But and then there's a rather different idea in the Yang and Barber paper. But I think that's, as far as I can see at the moment, that seems a little bit confined to the one-dimensional case. So again, I think there are open questions about uncertainty quantification in higher dimensions.
Any more questions? Okay, if this is not the case, then let's thank Richard again. And we're just going to have a quick 5-minute break in case anybody wants to grab more food, which is over there, or more coffee, which is in the... So our second speaker this morning is Pierre Alquier. Thanks.
Okay, so first I would like to thank the organizers for this event. I learned a lot yesterday. Also, I would like to apologize because when I prepared my slides, I realized that actually the workshop is about approximating high-dimensional functions, and my talk is about approximating stuff and high-dimensional stuff, but definitely not high-dimensional functions. So if I want to be more clear, actually, it would be more about approximating high-dimensional probability measures. Okay, so the idea is that when you're doing Bayesian statistics, so assume that you want to estimate a parameter theta naught, okay, in dimension 1, but I will talk about high dimension later. So there is a ground truth here that you don't know, and usually you put a prior on that, something like, maybe it's a bit too good, this one, so I don't know, maybe something like that, okay, a prior. Okay, and then when the sample size grows, when you have observations, then you come up with a posterior distribution that can be a bit strange, but you expect it to concentrate around the ground truth, okay? The problem is that in high dimension, this one can be very, very hard to compute. So if you want to use, for example, many talks mentioned Monte Carlo method yesterday, in high dimension, it might be very hard to sample from this distribution. So there is a very popular idea in computational Bayesian statistics is to replace this distribution by an approximation. For example, here you can think of a Gaussian approximation, okay? So the thing is that for this black thing, there is a theory. How does it concentrate around the true parameter theta naught? And the objective of this talk is to derive a theory for the red one, for the approximation, okay? So this is based on a paper submitted a few months ago and written with my co-author, James Ridgway. So it was submitted actually such a long time ago that I think that we can expect a rejection for Christmas. We'll see. But anyway, so I will spend most of the talk actually introducing notations and explaining exactly the different kind of distances I'm going to use to measure the concentration around theta naught. Then I will give the main result, but it will be quite short actually once the notation will be introduced. And I will, in the end, provide a few applications if I have enough time. Okay, so just very classical notation in statistics. Okay, so you have a sample, x1 to xn, drawn from a probability distribution, p theta naught. And the density of p theta naught with respect to some probability measure, like the Lebesgue measure or a discrete measure, will be denoted by p theta, small p theta, okay? And as it's a Bayesian framework, you have a prior pi, which would be this distribution here, okay? So the likelihood, which measures the adequation of the parameter theta to the data, is as usual, okay? So the product of the densities, and it will be denoted by capital Ln, okay? And usually, this black thing here that people use in Bayesian inference is the posterior. It's a probability measure that is proportional to the likelihood and to the prior, okay? So I just choose, I don't want to use heavy notation, so I don't write explicitly d theta knowing given 1 to x1 to xn, okay? I just use pi index n, but remember that it means the posterior, okay? And actually, this talk is not going to use exactly the posterior. It's going to use what is called a tempered posterior, and it's something that is becoming more and more popular in Bayesian statistics. So you just introduce here something else, a power, alpha, between 0 and 1, that you take the likelihood to, okay? So there are many reasons, actually, for this, and the reason why I study this might not be the best one, but one of the reasons why this is so popular is because, actually, as it makes the posterior a bit flatter, it's easier to sample from it. So if you use Monte Carlo methods, it's good. I think that I would say that the best reason to use this is actually a recent series of papers by Grunwald and many co-authors, and actually there are other papers mentioned in our preprint, but this is one of the most striking one, I think. It's that it's robust to misspecification in the sense that if actually x1 to xn are not drawn to a member of this family, okay, this can work sometime and converge to the best approximation in this family, but sometimes it can do absolutely terrible things. And usually, it does not happen if you choose alpha carefully, actually. But the reason why I'm going to talk about this one today is that actually it's also easier to analyze this from a theoretical point of view, and especially the variational approximation we were able to derive convergence results in the case of a fractional posterior, but not in the case of the true posterior. We can discuss that later, actually. But okay, so first I'm going to explain how, for example, these authors use well, what theory they proposed to assess the convergence of the tempered posterior, okay? And then I will show how to derive the same results for the approximation. Okay, so what they use, actually, in order to measure distance here, is not the most classical notion of distance in probability distribution. It's called the alpha-Rényi divergence, okay? So it's a probability distribution given by that. And if you're familiar with it, good. But if you're not familiar with it, actually, it has, well, connections with more classical distances, okay? So all the properties of these things actually are derived in this very nice paper. It's very nice because you see all the properties that you might expect. Is it convex? Is it distant, etc., are derived in this paper by Van der Ven and Haremos. And the thing is that for statisticians, Kullback divergence and Hellinger divergence are more classical tools. And the point is that when alpha is between 1/2 and 1, this Rényi divergence is between the Hellinger distance and the Kullback divergence, okay? So actually, this is not a distance, but for example, when d alpha of P and Rn would tend to 0, it would still tell you that Rn converges to P because this here is a squared metric, okay? So it's still related to convergence. And when alpha tends to 1, this converges to the Kullback divergence, okay? And now this is the results on the true posterior, okay? So this result was proven by Bhattacharya, Pati, and Yang. And what they proved is, well, it looks a bit complicated, but you'll see that everything is quite simple to interpret in the end. The question is, does this probability distribution here, the black one, converges to theta naught? And what you do is that actually you look here at what you're interested in, I mean a neighborhood of theta naught, something very small, okay? And this neighborhood here is called B of R, okay? So it's a ball of radius R around theta naught, but the ball is measured with respect to this distance, okay? So it's not even a distance, sorry, but to this kind of criterion, okay? So it's the set of thetas that are close enough to theta naught in the sense of the Kullback divergence between P theta naught and P theta, okay? And there is another term actually, but it's related and just here for technical reason, and I will even remove it later, so don't consider this one right now, just consider this one, okay? So if you want, okay, your posterior here, when the sample size grows, to concentrate around theta naught, what you need is that actually the mass of the prior distribution, under the prior distribution of this ball is not too small, okay? And it's rather intuitive, of course, because it's clear that in this situation, if my prior is like this one, you cannot expect a concentration to theta naught, okay? So it's very intuitive. But still then, in the end, it also quantifies the rate. So here you have R, here you have R, and if you manage to find the smaller Rn such that this takes place, then you know that the posterior under so the P theta under the tempered posterior is going to concentrate around P theta naught at this rate, Rn. So you also have a quantification of the rate of convergence. Okay, and this is the good point, and this is where you hope to obviously, you have to work to compute this, and in the end, you hope to derive the optimal rate. Okay, so obviously, I mean, this looks obvious. Nobody would choose a prior like that in this case. But in high dimension, obviously, the mass is more spread out, so it can be difficult actually to lower bound a log of 1 over pi of the ball. Okay, so now, variational approximations. Why? Actually, now you have to compute this black thing, okay? And as I said before, there are methods, like for example, Monte Carlo methods. They work well, and they are valuable tools for, especially for, well, estimating theta naught, but also for uncertainty quantification. But the point is that most of the results on the convergence of Monte Carlo methods are asymptotics. And if you try to derive non-asymptotic bounds, unless in very favorable situations, you always have things that are not so good, and you have to wait a very long time. And in high dimension, actually, you might not even observe the convergence of your Monte Carlo methods. So given the fact that now there are very, very efficient approximation algorithm, that usually approximation algorithm, like optimization algorithm are much faster than Monte Carlo methods, people propose to use the approximation, the red one, the variational base approximation. So the idea is just that you don't consider all possible probability measures. You consider a restricted set of probability distribution that I will denote by capital F, and you approximate your tempered posterior, pi and alpha, by a distribution in F. Okay, so you just, actually the approximation is taken in sense of the Kullback distribution. So you just minimize the Kullback distribution between rho and pi and alpha when rho is restricted to belong to F. Okay, so first question, we know, even though it's not maybe efficient in all situations, but we know how to approximate the black one by Monte Carlo methods. Do we know how to minimize this? Is this feasible? And the point is that if you rewrite explicitly what it is that I mean by this Kullback divergence, so up to a constant, you obtain this. So you have minus the log likelihood plus the Kullback divergence between rho and pi. And it appears that first, in many situations, things, for example, of exponential models here, you would have a relatively easy form here for that term, okay? So it means that sometimes you can even have an explicit form for that thing, and I will provide a situation where you have an explicit form for the approximation. But even if it's not the case, if this is simple enough, you can expect that you will have efficient optimization algorithm like gradient descent or things like that. Okay, so popular examples are first the one I drew here, so a Gaussian approximation. Okay, so you just replace the problem of computing a probability distribution by finding a mean and a covariance matrix. But another one that is very efficient, and I will show an example later, is what is called mean field approximation. So actually this term mean field comes from physics, and I don't know physics, so I'm not able to explain. But still, the idea is just to assume that different parameters are independent. Okay, so for example, there were many mentions of ridge function yesterday. So in ridge function, you would have something like that. So the parameter theta would be g and alpha, and the function of interest is j of alpha dot x. Okay. If you write the statistical model on this and try to infer alpha and g, they won't be independent. But actually, to enforce the posterior to be independent, here you have g, here you have alpha, and it makes it easier to deal with from a computational point of view. So actually, this one explicitly used, even though I won't talk about it in the rest of the talk, but this is a typical situation where you can use this mean field approximation. Okay, so now what I want to do is for this, sorry, I remind the notation, pi, tilde, and alpha, so it is the variational approximation of the posterior, and I want to derive exactly this result, but for the variational approximation. And this is the result. So you can see that the formula here is exactly the same, but it's just that the assumption is slightly different, okay? And what does it say, okay? It says that there must be a sequence of probability distribution in the approximation family such that the Kullback distribution of p theta naught and p theta, the Kullback divergence, sorry, of p theta naught and p theta integrated with respect to rho n is smaller than Rn, and the Kullback distribution between rho n and pi is smaller than nRn. What's the interpretation of this? It does not look so simple, but just think, for example, of the case where rho n would be actually pi restricted to be Rn. Okay? Okay? In this case, this just says that, well, actually, as rho n gives all its mass to be Rn, then obviously this is always satisfied. Okay? And then this, it turns out that if you compute this, you exactly end up with this here. It's exactly the same. So actually, our result in the case where you consider rho n to be this thing is exactly the same as the previous one. But the point is that it might very well be that in the approximation family that you choose, F, you don't have this thing. Okay? For example, in a Gaussian family, you don't have prior restricted to a ball. So actually, our result is a kind of generalization. If you don't have like localized pseudo-posteriors in your approximation set, then actually the genuine generalization of the condition stated in the previous theorem is this one. You have to find a sequence that satisfies that and that. And the idea is still the same, actually, in the sense that the row n that you find must be concentrated enough around 2 theta naught, okay? And in some sense, not to be not to have a disjoint support from the prior, okay? So in some sense, it's a very natural assumption. It just says, if you want your approximation to be good enough, then you actually need that in your family of approximations, of possible approximations, there is something that is good enough. And you don't need more than that, okay? So actually, for those who are familiar with like statistics and bias and variance terms and overfitting, in this situation, there is, for example, no possible overfitting, okay? So if F is huge, like if F is the set of all possible probability distributions, then, well, obviously, in this case, the Kullback distance is 0. Rho here is this guy. And this theorem just becomes the previous one, okay? So you still have convergence. But the point is that, obviously, in this case, the approximation is not really interesting because it does not lead to a feasible algorithm. So the balance here is not between bias and variance. It is between, well, still satisfying this condition to ensure consistency, but trying to propose an approximation that leads to a good algorithm. Okay? So I will propose now 2 variants of these results. And the first one is just a weaker but simpler result. Okay? So the point is that this has an easy interpretation, but for me, this term is less easy to interpret. It's here for technical reasons, because we have this can be rewritten as an expectation, and we have to control the corresponding variance. But actually, if you only want here, instead of having a result that holds with large probability, okay, if you're ready to have a result only in expectation, you can remove this variance condition, okay? So if you just want to control the expected distance of the posterior, okay, pseudo-posterior approximation of the posterior, sorry, to theta naught, with the same rate, Rn, then you just have to actually take the Kullback distance here and here. You don't have to introduce this squared log divergence, okay? So it does not bring something new, but it's just probably simpler to state, okay? The next result, well, there's something, actually maybe I should come back to the first slide. I already mentioned misspecification, and usually most of my work actually are in situations where you have a statistical model like this one, p theta. You have a sample, and you don't want to assume that you know the ground truth. You don't want to assume actually that the xn, x1 to xn are generated from a probability distribution in this model. What you want to, so usually I just want to assume that, I just want to prove that what I do, the estimator I propose, converges to the best approximation in this. And actually in this talk, it's not the case. I really have to assume until now that p theta naught belongs to the model. I wanted to state a result in the misspecified case, but you will see that here it is actually. It's, in my opinion, a bit like the new Star Wars movies. So it exists, but it's definitely not as good as it should be. So the reason why is that now I assume what I said just for this slide. X1, xn is drawn from Q, but Q does not belong to the statistical model. And my target is theta star, that is the best approximation in the model. And under similar assumptions, what I have is, well, the same rate of convergence here, okay? But I have in addition, okay, this Kullback between Q and p theta star, which means that it's like the oracle inequality that we had in Richard's talk. The point is that in your inequality, you had a constant one. Here, I don't have a constant one, but it's even worse than that. Is that the measure here that I have is not the same as the one here. It's not on the same scale, actually. So, well, this result exists, okay. If the Kullback between Q and p theta star is very small, it still says something interesting. But from a theoretical point of view, my next objective actually would be to derive something with like Kullback, or Renyi, something that can be compared. So there's still room for improvement in this situation. Okay. So yeah, now I will talk about 2 applications, but as the theoretical part is almost done, do you have any questions so far, or is everything okay? Okay, so I have 2 applications. Only the second one actually corresponds to a real-life application, but the first one, I wanted to derive, to write the theory in, how can I say, completely from the beginning to the end in the case of Gaussian approximation, so this case here, okay? So it appears that in many situations, you don't even have to specify the likelihood completely. There are many probability distributions where actually this will give a very good approximation, okay? So this is not a very high dimensional situation. Just assume that theta is the set R to the P with P not too large, actually. And we use a family of approximations. So we use Gaussian approximations. The mean can be anything in RD, and the variance matrix can be restricted to a set G, but it belongs to, obviously, to the set of non-negative symmetric matrices. Okay. So we assume a regularity on the likelihood with respect to theta. Okay. So it's a kind of Lipschitz condition, for example, when P is equal to 1/2. So we assume that it is smooth. So this will be satisfied, for example, for a logistic regression. Okay. Okay, the Lipschitz constant can depend of x, and we have these notations for the expectation of m of x. We have to assume that it is finite. Okay, and in this situation, if we do the computations, it's rather easy. You just have to compute Gaussian integrals. It's rather easy, and in the end, it turns out that even when you take sorry, maybe I should insist on this notation. Fg here, the family of approximation, is parameterized by the family of covariance matrices that you allow. Okay, even if you take only a constant times the identity matrix, in the end you obtain a rate that is in roughly in d over n. Okay, so you have a concentration to the true parameter theta naught with a rate d over n. Okay, so it seems satisfying. The point is that if you want to implement this in practice, something happens, okay? You can rewrite here the criterion that we had to optimize. You remember, maybe, sorry, I should come back to this slide here, this one. And it appears here that you just have to integrate this with respect to a Gaussian distribution. And here it's the same, actually. The Kullback is an integral with respect to rho, so it's a Gaussian integral. And in order to approximate Gaussian integrals, well, as they can be written as expectation of function with respect to the random variable psi that would be Gaussian, then it means that actually you can use a stochastic gradient algorithm, okay? And you can use a stochastic gradient algorithm. So it means that at each step, you compute the gradient of the function that you wanted to optimize, okay? And then instead of using the expected form of the function, you just take the gradient with respect to one realization of psi that you can easily generate with your computer, okay? So in the end, this is the only thing that you have to compute. And if, in addition to the Lipschitz assumption that I made before here, you assume that, that I made here, you assume that p theta is, for example, convex and Lipschitz, then this is enough to ensure the consistency. But then, okay, there's a lot of assumptions, but in the end, you can use your stochastic gradient algorithm. So nothing new here, it's just a reminder of the stochastic gradient algorithm. But in the end, we end up with these results, and I was, even though there are, once again, there are many assumptions, I was really happy with these results, mostly because what you have is a concentration result for an approximation of a Bayesian posterior, but it's really a result on what comes out of the computer after k steps. It's not a result on an estimator that you have to compute using an algorithm that might take a very long time to converge, okay? After k steps of stochastic gradient, you know that in expectation, your approximation of the posterior pi n a k, okay? So this is really the one that comes out of the computer after k steps. It concentrates around theta naught at the rate Rn plus something in 1 over k, okay? 1 over square root of k. So it's not, obviously it's not very good, and if you're familiar with optimization, you know that under additional assumption like strong convexity, you can have faster rates, but still, these results, in my opinion, is interesting because it's the first time that you would find something like that, okay? So just pure non-asymptotic Bayesian result, okay? So now I have plenty of time to talk about my main example. So it's the matrix completion example. So I don't know if you are familiar with the matrix completion problem. This problem becomes very, very popular in statistics and machine learning about 10 years ago because of many applications, and including the famous Netflix challenge. So they had, they proposed a data set, okay, where you had like users and movies. So the users can be, I don't know, maybe you're in the Netflix data set, I don't know, our organizer, so Hemant and Hareta, and maybe I'm in their data set, maybe, and other people. And here you have movies, okay? So movies can be, obviously, I don't know, I cannot remember actually the name of the Turing movie. Imitation Game, yes. Imitation Game, and Star Wars 7 and Star Wars 8. Sorry about that, but I was really disappointed. So actually, you have to give marks between 1 and 5. And so what happens actually is that they have a database like that, Netflix. And each time you watch a movie, they ask you, well, can you give a mark for this movie? So 5 means really good, and 1 means really poor. So for example, I would say like 4 for 1. And I don't know, I mean like random things. I don't know, really, but just like that. And their goal was actually to be able to reconstruct the missing entries so that they can, if they guessed that, for example, this would be a 5, they would propose you to watch this movie. So they want to make sensible recommendations, so they want to propose you the movie, only the one that you're likely to enjoy, okay? So here is a kind of toy example version of this problem. I say toy examples because I have many assumptions that are not so realistic, but actually I can remove most of them. So I will talk about that later. I assume that there is a matrix M0, so this is the ground truth, the one that I don't know, okay? And the dimensions are here, M and P. So M is the number of users, P is the number of movies, and obviously you cannot assume that it's 100, okay? It's maybe millions, okay? It's huge. So it means that the matrix is absolutely huge. And what I assume is that actually the observations are, first, I draw indices, so individuals and movies uniformly, okay? So in the uniform distribution. And then I observe yi, that is the entry of the matrix plus a perturbation that is, for example, a Gaussian distribution, where obviously the expectation is 0 and the noise is sigma squared, and I assume to know sigma squared. Okay, so what can be removed and what should be removed, obviously, is the uniform distribution here, because it's clear that some movies, for example, are more popular than others and are watched more often. And obviously, the Gaussian approximation is not so good because here you only observe integers. Okay, actually, it's possible to remove this and this too, but it changes the analysis and makes it more complicated. So I really want to stick to the toy example. Okay. So in this case, actually, the Gaussian, it appears that thanks to the Gaussian distribution, the distance between the probability distribution on Y induced by 2 different matrices, M and N, actually is just the Frobenius distance renormalized by the dimension M and P. Okay, so it's a very, very simple thing to interpret, okay? So the point is that, obviously, well, in a general situation, if you just have an array of numbers, you cannot reconstruct it unless you have a kind of structure assumption. And in this case, one of the structures that was used by many machine learners when they wanted to test algorithm on the Netflix challenge, actually, was to assume that M0 is low rank, okay? I think it's clear why actually low rank is a good assumption in this situation. The point is that a low rank means that actually you can design a few users, I would say a basis of users or a dictionary of users, but that is quite small, and assume that most users in the data set can be recovered as a linear approximation of either a linear combination of the basis users. Okay, so it's quite natural, I would say. The problem is that first now, if I want to do some Bayesian statistics, I have to design a prior on matrices and a prior that would make probably low-rank matrices more likely to appear than the other matrices, actually, full-rank matrices. Okay, so I read at the Bayesian literature, and it appears that priors on low-rank matrices, it goes back to the 60s, actually, because there were econometric models where people used these things a lot. So the first case is where you assume that you know the rank, K. So you assume that actually there are 3 possible different users, and we are all linear combinations of these virtual users, okay? So in this case, you can factorize the matrix, M that is P times N. It can be rewritten as a P times K multiplied by K times M matrix, okay? And it appears that for computational reason, people decided to use Gaussian distribution on the columns of not N, sorry, of U, okay? So U dot L is Gaussian, and V dot L is Gaussian as well, okay? The reason why is that in this model then, if you look at the likelihood, it will be something like E to the minus something minus the product U V transpose, okay, and squared. And once given, when U is given, then V, this is Gaussian in V. And when V is given, this is Gaussian in U. So it allows to use actually the Gibbs sampler. So the reason why they choose a Gaussian distribution was not for theoretical reason. It was because it leads to a feasible algorithm in practice. Okay. So rather than this formula, I like this one as well because it tells you that N is written as the sum of K terms. Each one is a row multiplied, a column multiplied by a row. So it's a rank 1 matrix. So you have a sum of K rank 1 matrices, and obviously this thing has a rank that is controlled by K. And this, I think, gives a good idea to extend this to the case where you don't know K, actually. You want to infer K. So what happens if you want to infer K? Well, the first time I saw this thing in this very special model was a paper by Salakutdinov and me, and what they proposed to do was say, no, okay, don't take K small. We don't want to assume that we know K. So we take K as the biggest possible value, the minimum between M and P, okay? But what we do is that instead of taking a constant variances for the rows and columns of U, what we do is that we take a variance gamma L that is itself random. So what it makes here is that you have K terms here, but if you choose the distribution on gamma such that most of the gamma L will be 0, most of the terms here in this sum will be close to 0. And so you will have a matrix M that is, well, it won't be actually low rank, but it will be very close to a low rank matrix, okay? And for technical reason, here again, actually for computational reason, people used the inverse gamma distribution for the parameter gamma L. But the point is that if you choose B very, very small, then the expectation and the variance of this thing are very close to 0. And so actually you can expect that most of the gamma L will be very, very close to 0. And as the inverse gamma is actually an heavy-tail distribution, then a few parameters will be very large, okay? So it means that actually here you will have a few significant terms, and most of the terms will be close to 0. Okay, so what can we do from a theoretical point of view to analyze this model? There was a paper by Taiji Suzuki, who proved actually the convergence rate for this estimator. And actually, the convergence rate corresponds to the minimax lower bound. But the point is that actually he was not really able to use this. He had to truncate the support of M. Okay? That's not a big problem maybe in practice, but that was really surprising because in practice, this seems to work quite well, at least when it can be computed on small data sets. It seems to work quite well. And actually, with a PhD student of mine, Tetian Mai, we also wrote a paper on this model. And we had exactly, I didn't know actually the paper, it was 2 parallel work, and then we discussed about that later. We had exactly the same problem. We had to truncate large values of U and V. And then in this case, we were able to derive the minimax rate of convergence in this model. And actually, there was a good point is that we could remove all the assumptions, you know, like uniform sampling and so on. But we had to truncate the support. which was a kind of mystery. So in this case, the rate is given by that, okay? So the mean error of an entry, on an entry of the matrix M, okay? So M minus M naught, you take the sum of all the entries and you normalize by the number of entries, N times P. It's actually upper bounded by the rank of the matrix, of the underlying matrix, times the maximum between the dimension, M and P, over N, plus additional logarithmic terms, and it's not clear yet whether they should be here or not, actually. But there is a corresponding lower bound where the log is not, and we don't know if actually it's a problem in the proof in the upper bound or in the lower bound, okay? So is this good? Yes, of course. I mean, the minimax rate here is quite good because what you would expect if you did not have a low rank assumption, where you have to reconstruct N times P numbers, so you would have a rate in M times P over N, okay? But here, instead of this, which actually can be written like the minimum between M and P times the maximum between M and P over N. But here, instead of this, what you have is the maximum between M and P and just times the rank over N. So if the rank is much, much smaller than the minimum, then there is a huge improvement. And you can expect, obviously here, you would have to have at least as many observations that the number of entries in the matrix, but here you can have a much, much smaller number. Okay, so for example, if this is 1,000 and 1,000, then you have 1 million entries in the matrix, but just with, I don't know, 10,000 entries. If the rank is smaller than 10, then you can expect to have a reasonable reconstruction. Okay, so this is for the true posterior, and actually even worse than that, for the true posterior, truncated in a way that is maybe not so simple to deal with in practice. So question, is it possible to improve things with variational approximation? And the answer is, in practice, yes. Okay, so that was proposed immediately in the beginning, actually, because as far as I remember, this conference proceeding is one of the first, maybe the first conference where this Netflix challenge was proposed, actually. And Lim and EYT proposed an approximation where actually you just assume, to make life simple, that all the rows of U, all the rows of V, and all the variances gamma k are independent under the posterior. So that's a lot, okay, of constraints. But it turns out that there are two things. First, you can compute, exactly for this reason here, you can compute the form, the explicit form of the distribution of U, V, and gamma. Okay, so not that this is a non-parametric approximation. You just impose the independence, but you don't assume that this is Gaussian. You don't assume that this is anything, but still, it appears that the optimal in this case is almost explicit. The rows of U must be Gaussian with a given mean and variance. The rows of V must be Gaussian, and the gamma k's are still, sorry, there is a typo, are still inverse gamma. Okay. The only things that you have to compute now are these mean and variances, okay? Well, there is no miracle here, okay? The problem is really hard from a computational point of view. So they proposed the fixed point algorithm, actually. It's written here, so I'm sure that you cannot read it from the last one, but actually you don't want to read it. You just have to know that it's explicit and it's possible to implement it. Actually, I tested this algorithm. It's rather fast. It converges to some fixed point, but obviously as the problem is non-convex and it's a really challenging computational problem, actually, you don't have any guarantee that you converge here to the ground truth. So I don't have a non-asymptotic results as I had in the case of a Gaussian approximation before. But still, it seems to work well in practice. And actually, we decided to use our result on this case, and it appears that it works well in the sense that if you assume that your matrix, the ground truth M is low rank, and that it can be factorized as a product U, V, where the entries of U and V are bounded, then using exactly this approximation by Lim and T, and not a transformed version, not a truncated version, then we obtain this rate of convergence, here constant times Rn, and Rn is exactly the rank of M times the maximum between M and P over N, so I mean the minimax rate of convergence. Here again, maybe up to log terms, okay? So as I said before, actually, the parameters in the inverse gamma distribution, you remember the one that generated the variance, have to be, actually A has to be taken as a constant, and B has to be taken as something very, very small. So actually, it does not really have to be exactly that number, but it has to be really, really small if you want to be able to derive such a bound, actually. Okay, so just one thing in order to close the loop. This is about the variational approximation. But obviously, as the set of variational approximation is included in the set of all probability distribution, as a corollary, you immediately have that the pi at n alpha, so I mean the true posterior, also converges at the same rate, okay? So it means that, in some sense, even though we have stronger assumptions, but it allows to remove this limitation here, like the truncation of the support of n and of u and v that appeared in the previous papers for technical reasons, okay? So you recover the rate of convergence for the true posterior and for the variational approximation that is used in practice. Okay, so maybe I was a bit fast, but this is it. Thank you.
Are there any questions?
Hi. So looking at your finite sample convergence result, I didn't quite understand one thing. So the objective function is highly non-convex, right? And then you typically get lots of local minima. So I guess, does this result somehow say that if you're converging to any of the local minima with high probability, because typically when they use iterative algorithms in this case, right, they actually observe empirically that there are many local minima and they observe to different ones on different runs.
No, the first example was about a really simple situation. Here, f is convex, okay? And the way we parameterize the variance in the Gaussian distribution make sure that actually this here is convex as a function of m and c.
Okay, so this particular
Obviously,
case...
if this is not convex, then you will have like this local minimum problem.
Okay.
And this is actually what happens in the matrix case, for example.
So then you observe this as well, that you really get local minima. The second question was, I didn't quite understand why this doesn't apply to the full Bayesian case. I guess what's the difference?
Yes, okay.
Maybe you could comment a little bit on that.
Actually, I have many things to say about that. The first one is, It actually goes back to the result we use, because our approach, some parts of the theory that we derived are based on these results. And here you can see that when alpha tends to 1, we are happy because d alpha converges to the Kullback divergence, so that would make a stronger result. But here, the bound tends to infinity, so it's meaningless. And this is really a technical limitation of the tools that we use. It cannot be used in the case where alpha is equal to 1. So I know that there are, for example, for the true posterior results, like a paper by Kochal, Ghosh, and van der Vaart, where you have concentration in the Kullback sense of the true posterior. But then in this case, you have this assumption, and you have another additional assumption, actually, the one on the existence of tests, to make, to be sure that you can test one parameter against the other, okay? So actually, last week, appeared a paper on the archive that makes exactly what we did, but in the case alpha is equal to 1, so they replaced this here by Kullback. Here they have alpha is equal to 1, but they have another additional assumption that is related to the existence of tests.
Okay.
So I can provide the reference if you want.
And is it sort of that heuristically it's automatically satisfied with these fractional posteriors, or I guess why don't you get this extra condition? Is it just?
It's also that the objective here, in some sense, it's easier in the sense that there might be situation, and actually I think that all the counterexamples that you will find, for example, in this here, in this kind of paper, are based in such situations. The point is that it might very well be that this quantity is infinite, while this one is finite. Okay, so.
Thank you.
Any other questions?
So in this matrix recovery example, given that you gave us this example with Netflix, so how does this compare to the simple alternating least square algorithm?
This is actually, if you
or maybe also, where does actually the whole setup you have here with this Bayesian, where does that actually differ from just saying I have a low rank matrix and I try to approximate the singular value decomposition
Okay,
of that thing.
so you could use, actually here you're right, you could use an alternate least square. Okay, so the point is, actually this is almost what this formula says. Because if you have a look at it here, you have something that really looks like, for M, for example, like you have a covariance, an inverse covariance matrix here, multiplied by the correlation Y with the entries. So it is actually a least square estimate. In the covariance matrix here, you have additional terms, so it's like more like a ridge, alternate ridge regression. Okay, so because if you write this, you would have e to the minus the sum of the yi's minus sum of k of u I k v k l squared plus, because of the Gaussian thing, you have u squared plus v squared. Okay, so if you try to minimize this, you have something that is, sorry, minus and minus here probably. Yeah. You have an alternating ridge regression. Okay. Now, well, why do people use Bayesian inference? Because instead of frequentist results, probably what you hope is that the covariance here also gives you an uncertainty quantification. But I would say, although the good thing is that in alternating least squares, you have to know the number of terms here in advance. And the Bayesian method that we proposed has this adaptation with respect to the number of non-zero terms in the sum here. And so you have the rank adaptation. And you can probably derive a similar thing in alternating least squares, but it's not immediate.
So what comes out then there when you run your algorithm on the Netflix data set? What rank do you estimate?
To be honest, I did not try on the Netflix dataset. I tried on the free version, the movie lens dataset. It's a bit disappointing on the smaller version where you have 100,000 observations n, because the rank is between 2 and 3, and then all the terms are negligible, which means that actually we are all combinations of two basic individuals. But there is, I don't know if you know this movie lens dataset, actually it's a dataset made by academics to replace the Netflix dataset, because the Netflix dataset, there was a trial about that because it was possible to recover very private information from it. So this is a dataset made by academics, and the idea is that you contribute freely. You say, I want to rate this film, this movie, this movie, this movie. And then they have 3 versions of the dataset with 100K, 1N, and 10 million ratings. And on this dataset, we find a rank between 2 and 3, but here it's about like 7 or 8. And I did not really try on this one, just because I'm a poor coder, but I'm sure it was done by the authors of the paper I mentioned, so just have to look at their results.
Is there any guidance to how you would choose the alpha when you're using this?
This is a very good question. Yeah, it's not so easy actually. So in a more recent paper by this author, Peter Grunwald, actually he managed to get a theoretical result proving that in a misspecified case, there is always a threshold, theoretical threshold, alpha naught. Okay, so if you're below alpha naught, then you're robust to model misspecification. But if you're above alpha naught, then there is at least one misspecified case that will make your estimator absolutely terrible. Okay? The thing is that this is based on assumptions that are, well, satisfied very often, but really not easy to compute. So I would say to derive this alpha naught in practice is really not easy. So no, really in practice, I don't have anything else than maybe just try to do some prediction and try some cross-validation or something like that. I don't have any better advice than that.
Okay, but you would say in general it's better to choose alpha too small rather than too large?
Yes.
From the result you just said?
Yes.
Okay.
In case of alpha too large, you can have some overfitting. In case of alpha too small, then, well, you may be a bit slower to converge, but at least you cannot have a big mess.
Any other question? So I just had one question. So you considered matrix completion, but if you have this other measurement model where you take linear measurements of the matrix,
yes,
which is something which is also
like Gaussian measurements, for example, or
any sub-Gaussian measurements.
Yes,
so you can still apply the same framework, but that would require extra work. You're saying it doesn't like just follow immediately, or
No, actually, it's almost in this case, it's okay. It would work in the same way, actually, really. So not in this paper, but in another paper, kind of older and previous version of this work, I considered very, very possible, very various measurement, and it's possible, I think, to include sub-Gaussian measurements, like something where you would have like xi that is a sub-Gaussian matrix, and you observe, sorry, the trace of xi transpose and not something like that. Yes, yes, this is possible to take this into account.
But then I guess you can also do this sparse vector recovery, or
yes, yes, yes.
That's also or sparse plus low rank matrices. So all those things will work.
Yes,
You just
yes,
change the prior in that case.
This is possible. Actually, once and these are examples we dealt with James in a previous version of this work. So yes, yes, yes. Sparse vector estimation was done.
Any other question? Okay, let's thank the speaker once again. from UCL, and he will be talking about efficient principal score estimation with kernel exponential families.
Hi, thanks. So the title is maybe a little obscure if you're not familiar with some of the settings, but I'll explain what it means, of course. So this is another talk that maybe doesn't quite fit as exactly with the topic of the workshop as some of the other things, but it's on theme-ish. So what we're trying to do here is we want to do density estimation. So we want a model for densities that is non-parametric and flexible, can handle complicated situations. We also want it to be computationally reasonably efficient to be able to actually use it in practice. We want it to work in at least moderate dimensions. And we want statistical guarantees for how well we're going to work. And as kind of an analogy, for at least for the first part of this set of desiderata, there's, in kind of machine learning communities, there's this, also statistics, there's this history of, you can take, like, for example, a Gaussian, and you can turn it into a much more complicated model by this more complicated non-parametric model by turning it into a Gaussian process, right? And you can take a finite mixture model and turn it into this non-parametric Dirichlet process mixture model, right? So what we're going to try to do here is take a generic exponential family type of model, which is obviously much richer than just a specific Gaussian, and do an analogous process of making it non-parametric and more powerful. Okay, so just as a quick reminder, exponential families are this kind of class of densities that you can write in this form. And so here the kind of standard parameterization, just as a reminder, the density at a point x is going to be determined by some function t, the sufficient statistic at that point, inner producted in, like, say we have s sufficient statistics, we'll take the inner product of that with some natural parameter. And then whichever particular distribution we have from this class is determined by this natural parameter. Then we also need a normalizer, and we have this base measure thing that is not super vital, but it is somewhat important to the model. I can talk more about that later. So for example, if we want to take a Gaussian distribution, the sufficient statistic there is just going to be x and x squared. If we take a gamma, it's going to be x and log x. And many other distributions you can get by using different sufficient statistics. Now the density only looks at the data through this sufficient statistic, actually through the mean of this sufficient statistic. And so it makes sense that if we want to try to make this distribution richer, we're going to need to be able to look at the data in more complicated ways than just looking at its first two moments, for example. So how are we going to go about doing that? The path that we're going to take is by putting this sufficient statistic, raising it from this S-dimensional object to some kind of object in what's called a reproducing kernel Hilbert space. And so just as a reminder for how these kernel stuff work, probably some of you are very familiar with this, but maybe some of you less so. A kernel, for our purposes, is going to be some function that's kind of intuitively like a similarity function between two objects. And the kind of default example is this kernel, has many names, Gaussian, square exponential, exponentiated quadratic, some others. That's just this, you take the difference, the distance in squared norm between the two inputs, scale it by some bandwidth, and pass it through a negative exponential. So this is what the kernel function looks like. This is one example. For any kernel function that's positive definite, there is some reproducing kernel Hilbert space of functions from x to the reals. And the key property of a reproducing kernel Hilbert space is that this kernel can be written as the inner product between these feature maps kx dot. And so this notation kx dot is basically, it's just the feature map of x in this Hilbert space. And the dot here means that this is a function. And so if we apply this function kx dot to a new thing y, that gets us kxy. You could also think of it as just like a phi function from x to h. Now, this Hilbert space is a space of functions, of course, and the kind of functions that you can get out from it are these linear combinations of, sorry, the phi should be a kx dot. They're linear combinations of these basis sufficient statistics, these basis feature maps. So, for example, one way, like some functions that we can make in this Hilbert space, kind of the smoothness assumptions that we make in the Hilbert space, are we can choose some of these like basis points, these big x's, drop these kernel functions at them. Then we can scale those kernel functions by some arbitrary scalar, right? So now we have a bunch of scaled kernel functions, and we add those up. This is a function that is drawn from this Hilbert space. And you can get many other functions of many different shapes by doing it the same way. All of these in this picture have the same xa points, but you can put the xa points wherever you want. You can have different numbers of them. You can have infinitely many of them, etc. So this is just kind of given a choice of kernel, this specifies the smoothness class of functions that you're going to care about and how you can represent those functions. And now there's another key property of these RKHSs. This is the R part, the reproducing part, which is just a very simple to derive given what I've assumed already, that if you take the inner product of some arbitrary, so you have some arbitrary function in the Hilbert space, technically this is just something in a dense subset, but whatever. It's written as a linear combination of these kx dot things. So if we then take its inner product with kx dot for some test point x, here's the inner product, just substituting in the definition of f here, just rearranging the inner product, we can, and then using this property that the inner product of the kernel functions evaluates it, we get that inner producting this kernel function with any function in the RKHS evaluates the function. So this is like the evaluation functional. So now we have this structure of RKHSs. We're going to use this to plug into the exponential family. And specifically what we're going to do is we're going to take this general form for the exponential family where we have our sufficient statistics and our natural parameter. Our natural parameter is just going to be some function in the RKHS, whatever function we want it to be. And then our sufficient statistic is going to be this kernel map of the point. So taking that, just changing the names here like I wrote them there, this is what we get. And then using this reproducing property that we just derived, this is just kind of a simplification of what this class of densities will look like now. So we now have this class of densities that are a generalization of the exponential families based on evaluating functions in the Hilbert space. So of course, if we want to cover a like regular exponential family, all we have to do is choose the kernel to be the inner product of the finite dimensional sufficient statistics that we have before. So we can get a Gaussian distribution by using this kernel. That's fine. But if we use a more powerful kernel, then we can get much more complicated forms of distributions. So there's this result that if you use something that's called an integrally strictly positive definite K, which, for example, the Gaussian kernel is, as long as that kernel decays to 0 at the, like, as you go out to the tails of the space, the kernel decays to 0, then it turns out that this exponential family is dense in the set of all distributions that decay, that have tails like this Q0 function, this base measure. So if you choose, say, a Gaussian Q0, then any distribution that is, sorry, I forgot to say this, it's got to be continuous too, of course. Any continuous distribution that does whatever it wants in some region and then eventually has Gaussian tails will be a member of this family of distributions. So what I've plotted here is just some examples of some of the shapes we can get. These are the same shapes as before, just passed through an exponential. So hopefully you believe now that we can get very complicated shapes of densities in this class. It's a rich class of densities, and it makes sense to want to estimate in it. Okay. Now that we have this class of densities that we want to be able to use, how do we actually use it? Given some samples, how do we estimate what the natural parameter, this f function, would be that approximately matches the distribution that these samples were drawn from, right? So, of course, the standard thing that people would do for density estimation is maximum likelihood. But that's hard in this case for two reasons. So there's kind of two different ways that you would normally do maximum likelihood in a setting like this. One is to just like write it down as an optimization problem and just do gradient descent or something like that. But the problem here is that this normalizer, this A of f, is hard to compute. You basically have to just numerically integrate to compute it. So that, if trying to do that at each step of the optimization problem is not going to be reasonable to get out an estimate. So doing like numerical optimization maximum likelihood is going to be intractable. The other main way you would do maximum likelihood, especially in exponential families, there's this really nice result that you can get the maximum likelihood by just solving these equations of matching the sufficient statistics of your data. You end up picking the parameter that matches the sufficient statistics of your data sample. But actually, for these rich classes of kernels that we want to be able to use, this problem is ill-posed. There actually there is no natural parameter that will exactly match the sufficient statistics of your data, because it turns out that the sufficient statistics it's called the kernel mean embedding, is such a strong description of your data that the only distribution that would match the sufficient statistics is just the empirical distribution of your data set, which of course the discrete empirical distribution is not a member of this class. Yep. Okay, sure. No, it's something that we assume we've fixed. You can then... Yeah, so that's the theoretical setting is you fix some smoothness assumption K and then fit within that. You can then, as a kind of outer loop, try to pick a K that fits your data well. But in the abstract, you would choose it based on prior knowledge and stick to that. Okay, so we can't do maximum likelihood because, well, for these reasons I just said. So we need some method, if we want to use this class of distributions, to estimate within it some other method than maximum likelihood. And the approach we're going to take is an approach that can fit these unnormalized probabilistic models without worrying about the normalizer. Then if we want to do something with the fit that requires the normalizer, we can estimate that with numerical integration once we have a fit, and then we only have to do it once at least. And that's obviously much more tractable than doing it at each step of a numerical optimization procedure. But for lots of applications, we also don't even ever need to normalize. So for example, we can use an unnormalized model to find modes, to sample from using MCMC type algorithms, and some other applications. There's also, so that's what we can get with this thing that's sometimes called the energy in deep learning, just this unnormalized log density. We can also do, just with the gradients of the unnormalized log density, which is sometimes called the score, we can do some other interesting things. For example, we can run, if we have a situation where we can evaluate log likelihoods but not gradients of it, then we normally wouldn't be able to do efficient samplers like Hamiltonian Monte Carlo. So there's an approach that I'll talk more about later where you can run an approximate Hamiltonian Monte Carlo using an estimate of the score in situations where you can't evaluate those gradients. You can also do things like, Chris has a really nice paper from a couple years ago where you can use this score functions to construct control functionals for kind of variance reduction in estimating integrals. So you could imagine using a score estimate like this in a setting like that too. But again, this is all assuming that we have some way to fit a parameter function f. So how do we do that? We're going to use an approach called score matching, which is, was proposed in this paper 10 years ago. It's actually, I'll talk about what the method is. It's also, if you're familiar with Stein's method, it turns out that it's closely related to that, though I won't talk about the connections here. Okay, so I'm going to talk about score matching just in this particular setting, which was proposed in this paper. So the idea of score matching is, instead of maximizing the likelihood, we're going to minimize the Fisher divergence. And the Fisher divergence is defined as the expected difference under the true data distribution between these score functions, the expected L2 difference between these score functions under the true data distribution. And now the reason that this is nice is that if we make some assumptions about things decaying to 0 at the boundaries of the space, then we can just do integration by parts and rewrite this loss as in this form. So this form now, we've turned these gradients, we've basically moved one of the gradients to the other part. So notice here, to evaluate this original form of the score, it depends on the gradient of the true log density, which is what we don't know, right? That's what we're trying to estimate. But we can basically use integration by parts to move that derivative to the other part, to the second derivative of the model. And of course, the model is what we know. So we can evaluate second derivatives of that, and then also squared first derivatives of that. And then it only depends on the true data as an expectation under the true data. So we can just evaluate that with samples. And then there's also this constant here that depends on the true data distribution, but it's constant across all models, so we don't have to worry about it when we're optimizing. So this loss function, this kind of integration by parts version, we can then just drop the constant and estimate this expectation with a Monte Carlo average. More or less make sense? Okay, so now here's a loss function that we can estimate from data, and we can just minimize that. We're gonna regularize this so that we can, for all the reasons that you normally regularize. And it turns out that if we minimize this loss function over the class of infinite dimensional exponential families, the representer theorem lets us know that the true minimizer of this loss function over the entire space H will lie in this span. So basically what's happening here is, say our samples, say here we have, imagine we're in 1D, we have 5 samples marked by these black dots. The space, the subspace that our true solution is going to lie in is going to be the span of kernel derivatives centered at each of these data points, union with the span of kernel second derivatives centered at each of these data points. So we know now that the true optimizer of this loss function over the whole RKHS lies in this finite dimensional span. And then we can, so we know that the function can then be represented just as weights in on each of these basis vectors. And we can get an analytic solution to the optimal minimizer of this regularized loss like this. It ends up looking like this. So the optimal solution, it's some linear combination with some weights of the first derivatives, plus there's some simple closed form part for the second derivatives. I'm not going to write the equation up there because it doesn't really matter. But basically what the takeaway from here is, the solution is there's this weight vectors that we have to fit that I'll talk about in a second, plus this simple closed form thing. So the way that we find these weights for the first derivative part of the basis is by solving a linear system. This G matrix here is a derivative kernel matrix. It's ND, so N is the number of samples, D is the dimension, times ND, and it's a linear system in that space. So that's nice that we can get an analytic solution like this, but solving this linear system takes n cubed d cubed time. So for reasonably high dimensions, that's just unacceptably slow, right? We can't use that to scale to either large sample sizes or large dimensions. So our goal for the first part of this talk is then going to be to approximate this solution in a way that will allow us to get a faster solution without losing our statistical guarantees about the quality of the estimation. So the way we're going to do that is with this technique called the Nystrom approximation. So remember that the representer theorem told us that the true optimizer of our loss over the whole RKHS is in this big span, which has two ND elements. So the idea of the Nystrom approximation is we're going to pick some subspace in the overall RKHS, and then we're going to find the best estimator of the function in that subspace. So it turns out, using a pretty similar solution to what we had before, if this subspace that we're looking in has a basis of size m, then this solution takes nd m squared time. So of course, if hy is just this same basis as before, nd, then we didn't change anything, obviously. But if we can get away with, for example, little md, a basis of size little md, then we've improved the dependence on n from n cubed to n m squared. So if m is significantly less than n, then we've gotten better solution time, right? And if we can get away with, for example, a number that is just independent of the dimension, then we also improve the dependence on the dimension here. So algorithmically now, we know how to do this. The question is, how small can we get away with for our basis and still get good statistical guarantees about our results? And also the other question is, what subspace should we choose? The algorithm doesn't care as long as you can compute this matrix, which is just a kernel derivative matrix from the basis vectors of this subspace. But obviously, if we choose a better subspace, we're more likely to get a good solution, good approximation. So again, remember the representer theorem says we're in this span. One reasonable choice for a subspace to use in our Nystrom approximation is to pick some indices out of these ND elements, just pick some subset of them at random, and then use that as our basis. So take, just of this first part, this first derivative kernel matrices, kernel basis vectors, just take some data elements, some directions, some dimensions at each of them, and subset that as our subset that we're using. So in this picture, again, we have 5 data samples, but we're only using 2 of them as our basis. And it turns out that this other part of the representer theorem solution here, the second derivative stuff, doesn't really matter. You could include it in your Nystrom subset, but empirically it doesn't seem to help. Theoretically, it doesn't seem important either. So we just don't bother. There's another approximation that you could pick other than this one that I just said. So we're going to call this one the Nystrom solution. And then this one is called the light approximation by an earlier work that proposed this approximation without proving anything about it. Rather than picking a subspace based on kernel derivatives, just pick a subspace based on kernel functions at these points. So instead of our subspace looking like these kernel derivatives at each of the data points that we choose, just put a kernel function at each of these points. And now the whole space H, of course, is the span of all of these kernel functions at every possible point. So it kind of makes sense that this would also be a good subspace to use to approximate functions in the RKHS. Okay, so kind of an overview of the theory that we were able to prove about this. We are assuming the well-specified case, so there is some, the density that we observe samples from actually lies in the class of kernel exponential families. For the algorithm, for the paper I mentioned earlier, that doesn't do the Nystrom approximation. They were also able to prove theory about the misspecified case. It's just technically much more complicated, so we didn't bother going through with that. Probably it all works. We haven't tried. But in the well-specified case, and then making some assumptions about smoothness of the kernel and the density that match the assumptions that were made in the full data case, we then have some parameter that kind of determines how hard the problem is. I can describe exactly how this is defined if people care, but just there's this parameter theta that for the hardest problems is going to be 1/2, and for the easiest problems is going to be 1/3. So the lower, the easier. If we choose a basis of size n to the theta, that's at least of size n to the theta times d, and we decay our regularization parameter like n to the minus theta, then the Fisher distance between our estimated density and the true density is consistent, and it has exactly the same rate that that paper I mentioned earlier was able to show for the full data solution. So in terms of the bound on the accuracy, like the Fisher distance accuracy of our estimate, we get exactly the same rate as the full data thing, where we're choosing only n between square root n and cube root n, depending on the problem difficulty basis points. Now, in other distances, including like KL in either direction, Hellinger, total variation distances like that, for hard problems, we were able to show the same rate as for the full data case, but our rate saturates a little faster for easy problems. That's probably an artifact of the proof. Okay, so the vague idea of how to go about proving this, basically all of these distances can be bounded relative to the distance between the true parameter function and the estimated parameter function in the ArcHS. This like Hilbert space distance between them. So what we're going to do is we're going to define the best estimator in the subspace that we're using. So we're saying, ignoring the data points that we see, but fixing the Nystrom approximating subspace, the exact subspace that we're using, the particular data point that we're putting down the kernel functions at. Then we're decomposing the error with respect to like an estimation error within that basis and an approximation error from that basis to the overall best function. And the way that we bound to these things borrows a lot of results from this paper that did Nystrom bounds for ridge regression problems, because our estimation problem looks a lot like a ridge regression. We had to do some technical things, like we had to do a Bernstein inequality for these correlated operators that come up for the correlation across dimensions in this bound. But the proof overall is vaguely similar to this technique. The key thing for this approximation error is saying that, kind of bounding how well this subspace that we're estimating the parameter vector in, how well it covers the true density F0. And that's kind of the main part of understanding, like the difference between, for example, this light approximation where you use kernel functions and what we're calling Nystrom, where you use derivatives of the kernel functions. Okay, so that's the overview of the theory. If we have time, I can talk a little bit more about it later, but for now, let's go on to some experimental results. So before I describe the experiments that we did, here's the main approach that we compared to for this score estimation problem. There's this paper from a couple years ago that proposed doing the score estimation problem using a denoising autoencoder. So this is this deep learning method where basically you train a model to you take an input, add some noise to it, and then train the model to try to recover the original input without that noise present. And they proved here that if you do that with a normal noise of variance sigma, then this quantity, the reconstruction error divided by the noise converges to the score. There should be a log in there, the gradient of the log density. This is true as long as your autoencoder that you're using has infinite capacity, so it's capable of representing any function, and that you actually trained it to the global optimum in this hard non-convex optimization problem. And also, this estimate depends on the amount of noise that you add. It functions basically like a bandwidth parameter in the estimator. So this is the competitor method that we're comparing to. Okay, so now to evaluate how well this approach works, we're gonna do two classes of experiments. The first one is synthetic experiments where we design a toy problem and we know the true answer, so we can just compute how well we match the true answer. The other problem is this gradient-free Hamiltonian Monte Carlo problem that I'll describe more in a second. Okay, so here's the first synthetic problem. We are taking d-dimensional Euclidean space, put the unit hypercube, and then choose d vertices out of it. Then of those d vertices, drop a normal at them, and that's our distribution. So it's a mixture of normals at d vertices of a hypercube. So in 2D, this is what it looks like. And then here's what the score function looks like. This is the gradient of the log density, so it points towards modes. Each of these basically looks like an independent Gaussian, and there's a line in between where it picks between whichever one you're closer to. In 2D, this is very simple, right? It's just 2. But as the dimension increases, of course, the structure of this gets more complicated. Okay, here are results on the quality of the score approximations for different methods as we increase the dimension. So this dark blue line here along the bottom is the case where we're doing the full kernel exponential family with all of the data, no Nystrom approximation. Then these black and yellow lines at the top are the autoencoder method for different like sizes of the network. Both of them do pretty poorly compared to all of the kernel methods here. Then in between are these Nystrom approaches with different sizes of the basis. So the two lines here that have x's are the Nystrom using the kernel derivative basis, and the two lines with dots are the light approximation, where you put kernel values down. And we can see that in this case, if you use a decent number of, like a reasonably sized basis, a reasonably large basis, then we get essentially the same performance as the full data with either one. For a smaller basis, we get worse. And in this case, the light approximation does substantially worse than the one where you use the kernel derivatives. But in this case, we're using the same, just to clarify the difference between these lines. This line here, the Nystrom with the kernel derivatives, has 42 points times d dimensions in the basis for each one of them, whereas this light thing has 42 points, period, because it only uses one basis function per sample point in the basis. So the light method is actually faster, as we can see here. So this is a plot of run times. The autoencoder, as we use the settings recommended by that previous paper, is actually really slow on this data too. This is not, to be fair, this is not a method that was really optimized for running fast. But if you do most of the standard deep learning things to speed things up, the estimate, at least, so for example, this is trained with a full batch LBFGS. If you just switch to SGD, the estimates get really unstable and bad. So the full batch seems to be important, for example, and that's part of the reason why it's slow. Another thing to observe here is that on the log scale, of course, the full data is always the slowest. The bigger Nystrom that does well is slightly faster. The smaller Nystrom is much faster, and then the light things are also much faster. Okay, here's another synthetic problem quickly. So this is a case where we have 3 concentric circles in 2D with Gaussian noise along the radial direction. And then as we make this higher dimensional, what we're going to do is just add independent Gaussian noise in the other dimensions. So this is an interesting problem because it's more it has more structure to it than the previous grid example did. And in this case, again, the results look vaguely similar. The difference here is that in this case, the light outperforms the Nystrom with the dimension approximation stuff. Okay, so now here's another setting, which was kind of the motivating example for Heiko, my co-author, working on this originally. So this is the problem that I mentioned earlier, where we want to do a big expectation. In this case, we want to marginalize out the choice of hyperparameters for a Gaussian process-based classifier. In this case, you can estimate the likelihood of a particular set of hyperparameters using this expectation propagation algorithm, but you can't get gradients that way. And that means that you can't use these efficient Hamiltonian Monte Carlo methods that tend to be much better samplers than the random walk metropolis Hastings approaches. And so you're kind of stuck using the slower variants of MCMC. So this earlier paper by co-author Heiko suggested this, this way to approximate Hamiltonian Monte Carlo using one of these score estimators. So basically what you do is as you're running your sampler, you fit one of these score estimation models, like the kernel exponential family, to the samples that you've seen so far. That then gives you an estimate of the score function, the gradient of the log density, that you can then use to propose a trajectory in Hamiltonian Monte Carlo as if it were the true gradient. Now, of course, your score estimate will not be exactly right because it's based on an estimate, maybe with potentially a small number of points. But the nice thing is that because we can actually evaluate the log likelihoods, this metropolis rejection step that's part of the Hamiltonian Monte Carlo process actually just accounts for any problems in the score estimate. So if we have a really bad score estimate, then the Hamiltonian Monte Carlo step will just reject the bad moves that we propose and will be slower, but we won't be any less accurate. So the experiment that we're doing basically is we took this classifier on this UCI glass data set, and rather than running the full sampler to evaluate, which there's a lot of moving parts in that, and then evaluating how good your samples are also requires a bunch of choices in how you evaluate that, and it's just a big complicated process. Instead, what we're going to do is we're going to say, we're going to fit our model to a bunch of samples from something that we assume is basically the ground truth. Basically, we ran metropolis Hastings walks for a really long time and thinned them a lot so that we get samples that should be basically the ground truth. And then we track, we run our estimate based on those samples, and we track how good our estimator is by looking at the acceptance rate of HMC based on trajectories proposed by our score estimator. So if we have a good score estimate, then we should have a high acceptance rate. If we have a bad score estimate, then we'll have a very low acceptance rate. So here are the results for the different methods doing that. So this blue line is the full kernel exponential family. Here we get about a 60% acceptance rate. If we had the ideal gradients, it would probably be somewhat higher, maybe like 80%. It's hard to evaluate that because we don't know the true gradients. The autoencoder method does really poorly here. It gets like 5%-ish. So it's a really bad estimate on this particular problem. And then the Nystrom approximations, if you use a huge basis, you do as well as the full, unsurprisingly. If you use a moderately sized basis, you do noticeably worse, but still pretty good. And then even if you use a very small basis, which will then be extremely fast, you do substantially worse than you would have done with all the data, but it's still enough that it's a significant improvement over the previous method that you could use. And this is also, here's just a plot of, as mentioned earlier, there's some hyperparameters here in the choice of the kernel and stuff. You could this is a plot of the score function on this particular problem as a function of the hyperparameter. So this is the regularization amount, and this is the bandwidth of the Gaussian kernel that we used. So we can see that this is a pretty nice surface that looks amenable to optimizing those hyperparameters with gradient descent on a validation set. And doing that is something we haven't really explored yet, but that potentially allows you to use much more complicated kernels than the simple Gaussian kernel that could potentially model your data much more effectively, that would have some hyperparameters in them to use to kind of fit the data, that you could then optimize that with gradient descent rather than being stuck to the simple kinds of things that you can estimate with a grid search. Okay, so just to recap what we've done so far in the talk, we proposed this rich kernel exponential family model, which we can fit with score matching, but it's kind of slow to do that. We can instead do this Nystrom proposal to speed up the performance with guarantees on the same, you get the same quality of statistical estimation. There's also this light version, which, actually I guess I didn't explicitly mention before, I should have. Our theorem, we weren't able to prove a complete bound for the light thing, only for the case where you do the kernel derivatives. So the light version is even faster than what we were calling Nystrom, but we can't quite prove guarantees about that yet. So this was all based on this paper. Are there any questions at this point before I move on to the next part of the talk? Okay. So this is all well and good, but it's hard to imagine it scaling to really complicated distributions, just because this kernel smoothness kind of thing allows you to do a lot of shapes, but it does require your density function to be fairly smooth. So this paper now proposes to do a kernel conditional exponential family to take advantage of structure in the data. So a lot of times, any given data set, random variable, might have a graphical structure to it in terms of not all of one of these graphical model structures where some of the variables will depend on other variables in a tree structure. So you can, or a DAG structure in general. So this is always true if you just take something like this. You just do a big chain like this. You can always factorize things, obviously. And then there's this whole field, of course, of graphical models that tries to construct or estimate these models that will have more efficient structures than this, like fewer dependencies that the data actually follows. And a lot of times you can get that. So what we're going to do here is, rather than the typical graphical model setup where you assume that each of these factors is conditionally Gaussian or something, we're gonna estimate each of these factors as an as a kernel exponential family model, a new variant of them that can be conditional. And then each of these factors we can estimate independently and then multiply them all together to get a final model for this whole complicated data. So, for example, just as to understand the setup, we're going to say x is going to be some variable that we're conditioning on, and y is the density, what we're going to evaluate is the conditional density y given x. So we want, given this joint distribution, we want to be able to say the conditional density of y given x is -1 is this density curve, for example. And we want to be able to estimate that as a function of x. So how are we going to go about doing that? So we can take this same setup that we had before for the kernel exponential family and just replace the sufficient statistic that we had before with something that's a function of both x and y, right? And of course, the normalizer will also depend on x. This will all be conditional on x. So the particular way that we're going to do that is we're going to say, okay, for a particular x, we're going to have a natural parameter that depends on x, and then it's otherwise going to be a kernel exponential family, like we just talked about. So now this fx is the natural parameter for conditional on a particular x in a Hilbert space G, and then we have just the rest of the machinery exactly as before for the kernel exponential family. And now this feature map, this form that I put in the first equation, can be written in terms of the second equation by using a vector-valued RKHS. And what that looks like basically is we say this fx is going to be the outcome of some linear operator, gamma x star, on f, which we can then convert into an operation just by moving the adjoint around on this original Hilbert space H, which is going to be a vector-valued RKHS. Okay, so what do we do to fit in this conditional model here that we care about? Well, the first thing that would make sense to do as an analog of score matching would be to minimize the score, the Fisher divergence, between the joint distributions, right? So this true density of x times the true conditional density of y given x from the model's marginal density of x and conditional. The problem with doing that is that this expression, though it doesn't depend on the normalizer for x, which we can't compute, it does depend on the normalizer of y given x. So for all the reasons that we couldn't do it in the regular kernel exponential family, we can't do this here either. So instead, we're going to propose minimizing this kind of expectation of conditional divergences. So what this loss function we're going to use is we're going to put some distribution over x, which maybe ideally would be the true marginal, but it doesn't actually really matter what it is as long as it covers the actual support of x. And we're going to look at the expectation of the Fisher divergence between the conditional distributions. So if this is 0, then for this to be 0, of course, because it's an expectation of a non-negative thing, each of these things need to be 0, at least for pi almost all of them. That would mean that the conditional distributions match almost everywhere. So that's good. It also, I'm not going to write up the equations, but minimizing this gets you an estimator depending on the form of your, if you assume an RKHS conditional form for the way that these fx functions are related to each other in kind of a natural way, then you get a minimizer that looks almost the same as it does in the non-conditional case. So that's also nice. Here's a problem, though, with this loss function. Here's a case where it doesn't really work as you would want it to. So imagine we have this distribution, which here's the distribution of y given x equals 1, and the distribution of y given x equals -1. And we're going to say we have a discrete distribution on x. It can only be 1 or -1. Now, here's the marginal distribution. If we say that x is equally likely to be either of these two things, it's just the average of these two densities, right? Now, the problem is that our loss function, the expected Fisher divergence between these conditionals, is actually 0 here, which contradicts what I just said about it only being 0 if they match. So, sorry, to clarify what I just meant, is the loss function between this conditional distribution and the distribution that ignores the conditioner and just gives you the marginal on y is 0. Now, the reason for that is, remember, our loss function is this expected conditional divergence, and then this Fisher divergence is the difference between these score functions, so the gradients of the log densities, when it's 1 from when it's this marginal. So if we look at that, just for the case, imagine when it's 1, so over here, we're comparing this distribution, the red distribution, to just this part of the teal distribution. This part of the teal distribution doesn't show up at all because we're taking expectations in the case, we're taking conditional expectations on x being 1, so we never evaluate this density over here. And now these two densities are exactly the same as each other, except that this one is half of the other. But remember, the whole point of this is that we don't care about the normalizer. We're not worrying about the normalizer at all. So this is 0. And then the same thing in the other case. So our loss function is 0. Now, the reason that this happened is that when I said before that it's 0 if and only if they always match, is that this situation actually violates the assumptions of the theorems that are proved in this paper. But, so in some sense, oh, we don't have to worry about that. It's not really an ArcHS, whatever. But, of course, it's possible to get a real situation that approaches this. So you need to be really careful when you're using these models that you don't end up in something close to this situation. So that's a problem with them. But here's some experimental examples anyway of just applying these conditional models and hoping that problem doesn't come up on 2 data sets. So here's 2 example data sets. One is Parkinson's, which is a distribution of some various like measurements of aspects of recordings of people's voice when they have early stage Parkinson's, which maybe it's not yet noticeable to someone looking at the person or listening to them talk, but it turns out that there are actually markers that you can detect in the acoustics of their voice that they're starting to get Parkinson's disease. And then the other data set is this red wine data set, which is measurement of a bunch of chemical aspects of some wines. So these are 15 and 11 dimensional, and they have a few thousand samples each. So they're not hugely high dimensional or huge numbers of samples, but they do have these kind of sharp structure to them. So they're a good example for evaluating our models. Okay, so if we look first at the negative log likelihoods, so that smaller is better, and compare it to some of these other 2 methods. I won't talk about them in detail, but this is a least squares conditional density estimation method that has some theoretical guarantees. And then there's also the neural, I forgot what the R is. Anyway, it's an autoregressive, there shouldn't be an R. That's why. I don't remember what it is. This is the neural autoregressive density estimator. So this is like a deep learning-based autoregressive model. So if we look at negative log likelihoods, we can see here that on Parkinson's, our conditional model does better than the other 2. On red wine, the neural one does a little bit better, but we're kind of comparable in terms of likelihoods. And both are much better than this conditional density ratio estimation-based model. What do the samples look like? So here's 2 of the dimensions out of, I think it was 11 for this red wine data set. The black here are data samples on the marginal on these 2 distributions. And the red are samples from a kernel exponential family that's just fit on the whole thing, nothing conditional. So we can see that it does basically, it gets the basic shape right, but it also has a bunch of stray points here where the true data doesn't have any support, right? So it doesn't quite match the distribution that well. Whereas the conditional model does a much better job. It gets these sharp lines much more effectively while putting very few samples kind of out in this region where the real data doesn't have any samples. The same kind of thing is true here on the Parkinson's data. The kernel exponential family model does okay, but it's kind of over dispersed in the region where there's no actual data, whereas the conditional model does a much better job of fitting to these sharp boundaries. Okay, so just to recap overall, we have these models. The Nystrom manages to give us speedups with guarantees on the performance. The conditional model manages to get us to these more complex models. They're really easy to plug into each other to get both, though we didn't quite do that yet. And you can still get some theory on this density estimation stuff in a more complicated setting that's reasonably practical. So that's it. And you can ask some questions if you have any.
Any questions?
Sorry, just going back to your sampler where you were looking at the speed of the Nystrom approximation, where you had, I think, M was 10 or something.
This one, yeah.
Did you look at the number of effective samples as a function of computation time?
So, so for this paper, we didn't do that because we didn't actually run the sampler. Just out of kind of, there's a bunch of moving parts getting all of it to work. For the previous paper, this paper where they proposed it, I think they did measure the number of effective samples compared to a straightforward random walk sampler, and they did better, even in the full data. Or actually, sorry. So in this case, the full data thing is too slow. That was actually why they proposed this light approximation in the first place. And the light approximation did, I think they measured effective samples using the normal effective sampler. They also measured, in this case, they measured like convergence of the target, of the distribution to the target using MMD as a measure of distance between the distributions. And they did much better in MMD score than just running a regular Metropolis Hastings for the same amount of time.
Any other questions?
Thanks for an interesting talk. I wonder if you could comment a bit more on the kernel exponential family, because the examples you gave on one of the first slides, where you had a Gaussian mixture and then you had a Dirichlet process mixture.
Yeah, sure.
So these constructions are about putting lumps of probability vaguely in areas that you think might be interesting. They're not really focusing on smoothness, although they're sort of infinitely differentiable models. But the kernel exponential family is a bit different because it's all about smoothness, and it, in a sense, it defaults to a uniform as opposed to, point masses. Do you have any thoughts on that?
Well, I wouldn't say that, for example, a GP you can think of as largely about smoothness if you're using it for like a regression type thing, right? That's a little bit different in that it's not a density estimator, but like a regressor or whatever. But the way that I would typically think about a GP is as a kind of like an interpolator based on some smoothness model. And this kernel exponential family is in some sense similar to being an interpolator based on the smoothness in your RKHS, right? So it's not the same thing as doing like kernel density estimation, but it's kind of, it's related to the idea of just putting some mass where you see data and interpolating between them, but it's different from KDE in a lot of ways. But it is kind of a smoothness-based thing, I feel like, as a GP is. A Dirichlet process is a little bit different.
Do you think smoothness is somehow less directly related to samples than, a Gaussian mixture where you're just putting mass?
Yeah, I mean, it is, right. So the analogy to a finite mixture model to a Dirichlet process is a little less, is less close of an analogy, I think. The idea here was more in terms of an infinite dimensional type thing rather than I don't think the smoothness analogy works well for a Dirichlet type thing.
Any other question? Okay, let's thank the speaker once again. So we now have lunch.